Then,
Thank you.
yeah, good afternoon, everyone. So my name is Reich. I'm working at the Fraunhofer Institute for Innovation Systems Software Engineering in Kaiserslautern, Germany. And more specifically, I am a project manager for projects in the area of model-based safety engineering, and in particular doing like industry knowledge transfer from research in classically in the area of functional safety in various domains like automotive, agricultural, industrial automation, and also medical projects according to the standards that are in place in this regard. But the more interesting bit I'm going to talk about also today is how we assure actually more innovative systems that contain high levels of intelligence and also cooperative safety concepts. So it was a perfect talk like my predecessor, which dealt with behavioral safety. So my talk is basically about how to operationalize behavioral safety at runtime by using safety models that are used at runtime, where the machine effectively thinks on its own about safety issues and tries to come up with a as performant as possible way to operate in various operational design domains. So what I have to offer today is, first I'm going to talk a little bit about the motivation of why current safety engineering techniques are not sufficient actually to assure high degrees of automation. And our approach to dealing with these issues is to shift parts of the models to the safety assurance to the runtime. And how do we do that? We are formalizing risk and capability models in order to teach the system how to think about safety issues and kind of come up with a continuous safety assurance at runtime. And in the end, I have a small video demo that hopefully works that intends to show you how a dynamic risk management looks and feels like. But first of all, I'd like to show you a small video, might be of a parallel universe where actually all the challenges that we have already talked about seem to be solved already. So just let this, watch it shortly. Maybe remember just a nice music in the background that unfortunately doesn't play in the stream. So what we've seen in this video is actually, people are actually, passing each other very, very closely. And so if I look at this from a safety engineering perspective, then actually I'm feeling more or less fear because, I have doubts whether like this will go on if we are driving like a year in this intersection, for instance. So one of the goals that we are having with automated driving is actually to kind of deliver a certain mobility performance to people. This means like people can go actually away from steering and from operating the car, and in the end, they still want to get from A to B and doing different things. And this at a very good performance, so to say. But if we're looking at the challenge and put ourselves in the head of a safety engineer, what we're doing nowadays in order to get safe behavior of autonomous driving, then it's effectively that we are trying to kind of thinking at design time a lot about how we optimizing our system in order to be safe. So this means in particular, we need to anticipate the context that our system will be in contact with all the time. These are other vehicles, this is the environment, so to say. These are other traffic participants like vehicles and pedestrians and so on, but also if we have cooperation in place, we can use collaborative knowledge for that. And we might also be able to, maybe control other systems in our vicinity. And having like anticipated the full context and all the situations, like the situation categories and scenarios that we have seen in the previous talk, then what we're doing is we are picking out the behavior for our system. We are implementing it for this anticipated context and make sure it is safe. But this has some problems, in particular if we're dealing with like high levels of intelligence being necessary in order to operate in very unconstrained environments as well. So this means like we are having a lot of uncertainty in place if we want to think of any situation that can occur, that we don't know whether we really covered the situation space both at design time and at runtime. And on the other hand, we also have uncertainties with respect to risk control availability. This means like we have certain safety capabilities that are integrated in our car, but we don't even know that, whether those safety capabilities will be available in all the situations where we need them. And there is a way out of that, and that is done nowadays. And this is actually that we are designing our system and our behavior so that it is safe in the worst case. Namely, in the worst case of all the situations that that our ODD consists of. And at the same time, if we are always expecting, for instance, like exemplarily spoken, Usain Bolt to jump out behind every parked car, this means like our car is ready for it. But in all the situations where the worst case does not occur, we have a very constrained system performance. And this is actually where what I'm going to show in this talk is addressing. And it is called dynamic risk management. And the idea behind this, that we are not trying to anticipate every situation and scenario that will occur during the system operation, but that we are trying to teach our system what is the relation between certain situation factors that are influencing risk and the final risk assessment on the one hand. So making this relation explicit in a maybe rule-based manner, and on the other hand, making like the influence factors for those risk control capabilities and their availability explicit somehow. And if we are having this information basis, so what is the risk of our situation? On the other hand, what are the capabilities that we are currently having to control that risk? Then we can also model the engineer's knowledge of what to do in which of those risky situations. And what we're then coming up with is a concept that is called dynamic risk management, which effectively means our system has a certain intelligence involved and kind of looks in the environment from the safety glasses on and looks for events that are safe, that might be an indication for safety criticality or not. And this means then based on certain those monitored events, we're analyzing risk and capabilities, we are performing certain reasoning activities, and then we are planning and executing adaptation in order to come up with a behavior that is below the accepted residual risk. Yeah. And on the other hand, that is performant enough to control to get the best possible situation performance out of it. And for executing this dynamic risk management cycle, there is some knowledge that is needed, and this knowledge is explicitly those rules that we have to find at design time. So one precondition in order that we can observe whether the behavior of a system is safe at runtime is actually that we need a specification of what safe nominal behavior means. And so this is, so to say, the step 0 of doing runtime safety assurance or analysis is that we have a specification of the safe nominal behavior. Example that I picked out for today is actually the RSS rules. It seems, I would think that this is familiar to most of you guys, which are effectively a set of rules that try to formalize both explicit and implicit traffic rules that people adhere to. And in this case, we have an equation that is expressing what a safe longitudinal distance between two following vehicles are, where the latter is, or the left one is the ego vehicle, and here we have a lead vehicle. But there also exist rules for other traffic situations. And those are derived based on kinematic parameters. So the big question here is, so if we are deriving a safe distance specification based on kinematics, then all of these parameters that we are seeing here, for instance, we need to somehow assume deceleration capabilities of our lead vehicle are in the current situation. And at the same time, we also need to know something about what are our capabilities that we have at the current situation, for instance, the minimum deceleration capabilities. And so it boils down to what are we assuming for those parameters in the current situation. And is currently done is actually a worst case assumption over the whole ODD. This means effectively we are looking physically what is the physical maximum deceleration that can occur. And this is what we're assuming in every moment. For instance, we're knowing, okay, our systems can decelerate typically with maximum 1.1 G or so. And then if we are designing our systems in order to be able to cope with that maximum deceleration every situation, and we are safe. And that is the reasoning behind choosing these set of assumptions, so to say. But we at Fraunhofer, we ask ourselves, can we do better? Because again, it is not always the worst case happening, so to say. So can we somehow detect what assumptions are true in the current situation? And this is actually what dynamic risk management is about. So we're trying to actually replace or enhance the current methods that are, so to say, dealing with the worst case from all ODD situations on the one hand by looking at, well, what is actually affecting in my environment what the situational risk is. And if we are looking at a car following scenario, then we are seeing, for instance, looking at our own human experience, well, so when I'm driving as a driver, then I would assume this red car not to brake without any reason, so to say. But I would say that the situation somehow around this red vehicle is actually forcing it to decelerate. So this could be, for instance, a truck that is driving with a much lower speed, or it could be like this blue vehicle merging into the lane just in front of the red vehicle, or it could be, for instance, a traffic jam that is actually forcing this red vehicle to brake harsher than in normal driving. So, and that is somehow subsumed with a braking intention that we are having, that we want to find out during dynamic risk assessment, but it is also related to the braking capability. And there we are also looking at physical inputs. So for instance, like whether a certain braking distance for this vehicle is effective also depends, for instance, on a road surface coefficient. And risk is not only about whether braking happens, but also how severe the collision consequences are if that braking is about to happen. And there, the usual models are typically dealing with that delta speed between vehicles, where we can get an approximation of what the collision severity might be. So this is the side where we're getting an idea as an ego vehicle, what is the risk of our situation. On the other hand, if we have a particular risk, then we can look at, given a risk, so meaning that the current situation, the red vehicle is braking with a certain amount of deceleration, or it is likely that this happens, we can look at, okay, what are my possibilities that I'm having in the current situation? And once again, this is, dependent on the parameters of my own truck or vehicle in this case. With trucks, for instance, the vehicle mass plays a role here, but we also have road surface frictions, which is dependent on weather and tire wear, for instance. And also we have road topology variables that influence what I can do. And also similar like to the risk assessment that we had on the right side, we can also look what is our environment doing. So for instance, an evasion maneuver is not possible if the adjacent lane that I want to evade to is actually either occupied or non-existent. So if I don't have like a shoulder lane, for instance, that I can evade to, then kind of my capability space is constrained. And so if we want to teach those kind of activities, capability and risk assessment to the vehicle itself, we need to somehow find a way to formally model those dynamic risk and capability models so that they can be evaluated at runtime. Starting with the risk modeling. So basically expressing how a certain behavioral hazard that our system may have at a certain point in time. How does this lead to an accident? And typically this goes over a critical situation and controllability aspects. And so today this is mostly done by using surrogate safety measures like time to collision, or for intersection scenarios we have post encroachment time. There are really a variety of different surrogate safety measures, which are basically all have in common that they are the critical situations. They are try to be found by using simulation. So this means we are kind of taking a scenario catalog, like my predecessor has talked about, and actually kind of computing the time to collisions for a lot of variants of the input variables for those safety measures. And then we are seeing whether we get an accident or not. And what is also interesting about those is that they are mostly removing situational context from risk modeling. So this we can see, for instance, we can compute the time to collision just based on the speed vectors and the directions of two cars. And then we are having a conflict point. But indeed, if we are looking at how humans judge risk, then we will see that actually the risk is pretty much dependent on whether this exact behavior is happening on an intersection, whether this is happening on a highway. So the risk judgment might differ in those cases. And this is also a major weakness of the metrics that we have nowadays, that they don't consider situational context knowledge, like described on the previous slide, sufficient. So they are much more worst case than they would need to be. There are also probabilistic variants of those where we don't deal with points and vectors, but we are dealing with spaces, so to say, that are overlapping based on probabilistic constraints that we're having. So how we could do that tomorrow is actually to really factor in situation knowledge. And this means like making situation class specific risk metrics that are explicit with respect to the situation that is occurring. So if we're looking at this simple intersection scenario where the ego vehicle should turn right and a pedestrian is passing the pedestrian way and the green light, then we could actually model what is the expected behavior of the ego vehicle, which might be, so to say, an abstracted functional model of what for instance, the traffic regulations demand of my ego vehicle in order to be safe. This means on a very high level, we need to determine the right of way properly. We need to determine the pedestrian presence at this space, so to say. And if we know that there is a pedestrian present, we also need to predict whether he is going or not, because if he is staying here, then we are allowed to drive, even if the pedestrian light's green. So this is, so to say, the expected behavior that we model for our ego vehicle. And a subsequent step, we are thinking about what are unsafe deviations that will lead to a pedestrian run over. And for each of those functional blocks, so to say, we are thinking about critical deviations. This means like me as an ego vehicle, I determine the right of way wrong. This means I have a confusion, and this might lead in the consequence to making something that is critical. Namely, if I misjudge that the pedestrian traffic light is, so to say, green, then this will lead me to driving there, maybe, if I don't detect the pedestrian as well. So, and for all of those principal deviations, there are a lot of influence factors that lead to those deviations happening. So these are really the situation factors that we want to make explicit. And so not going into detail here, but the general idea here is that we are making, so to say, the relation between those deviation influence factors, principal ones, explicit to the actual expected behavior that might come, for instance, from traffic regulations or from RSS also. And this is not a formal model right now, but what we are using in order to make these causal models really formal is actually we're using Bayesian networks, not only because they can be computed pretty efficiently at runtime, but also because they have the power that you can also propagate uncertainties. And if we are looking, if we're looking back at those influence factors, then all of those, it's not possible to perceive them perfectly. There will always be like a perception uncertainty with respect to those. And this is the reason why we are using those Bayesian networks to factor in perception uncertainties and propagating them to the behavioral risk. And the reason is that because if we wouldn't do that, we would get like a risk assessment, for instance, you should now maybe there's a high likelihood that we have a certain accident in the end. And if this assessment, so to say, was made based on very, very uncertain information, then actually probably we should kind of be a bit more worst case than we should if we have perfectly certain information or more certain information, so to say. And what we've developed there is actually a pattern structure that can deal with a variety of different situation classes. And yeah, so you see just a small excerpt of the different influence factors that we have just for the crossing situation that we've just seen. And these are then effectively fed into those behavioral deviation nodes, so to say. And in the end, we have a causal model that is allowing us to get an idea about risk under uncertain information. And yeah, we are also have put that, so to say, coined it with the name SINADRA. It's called Situation Aware Dynamic Risk Assessment. And it not only has the runtime aspects where we just get out a Bayesian model that we are inferring, so to say, at runtime. But yeah, the important bit from a safety engineering perspective is also that we make sure we didn't forget any of the situation factors, and we have a lot of we have the necessary confidence that we didn't underestimate the risk in our Bayesian network model. And for that case, what we are doing is we're taking as a principal input the ODD and an AV behavior model, and we are, by using design time, model-based design time safety engineering, we are kind of coming up with, so that looks like more or less like a HARA, but is much more detailed and does not only try to search for the worst case situation, but analyzes situation classes, so to say. And based on this sub-ODD specific risk causality model, we are, so to say, using the pattern that I've just shown and parameterize it with a situation factor distribution. This means, for instance, that we are exploiting the specifics of distributions. For instance, if we are in commercial areas, which our ODD consists of, then we have to much different distributions for pedestrian appearance, for instance, at different places, and kind of we can factor that into the Bayesian network by looking at what are the principal ODD subspaces that we are having, and what are the situation factor distribution for the influence factors. And this is all what we are kind of building a safety case out of. So coming up with a safety argument that comprises these activities and tries to make sure that the runtime model that we are inferring at runtime is, so to say, safe with respect to an argumentation basis. So we also just got a paper accepted that is describing the building blocks of this framework. And now, kind of having described how a risk assessment can work, meaning like how does a hazard related to an accident over the situation influences, like let's look at the other side, which is dealing, so to say, with the dynamic safety capability assessment. And there we have now researched and also applied, I think over a decade right now, the concept of conditional safety certificates. Model-based means to express variable safety concepts of our ego vehicles. So we can, for instance, think of in this situation where we have a car following scenario, we definitely have the emergency braking capability. So this is one example. In addition, we would also have the evasion capability, but let's exemplify the conditional safety certificates for the emergency braking capability. And this means that we first need an idea what is, so to say, the architecture of our capability functionality. So keep in mind that this is a safety functionality here that is somehow engineered at design time according to typical standards that we have, like the ISO norm. And if we're looking at the emergency braking capability, then we can, for instance, monitor our brake system itself for what is your current tire wear, for instance, what is your principal braking force that we can apply at all in the best case, but also in the current case. And if we are looking for the vehicle platform, for instance, then there we would maybe get some information about our dynamic mass that our vehicle has. This is much more important for trucks, obviously, but also we might look at the environment for getting an idea about the road surface conditions, which also affect how effective our emergency braking will be. And as a special feature, since we're using here a service-based modeling format, we can also use kind of vehicle-to-X monitoring functionality to also get information in an assured basis from a different vehicle. So this is effectively how the safety channel looks like. And the conditional safety certificate, so to say, is attached to this service architecture that we're seeing here. And it actually defines certain kind of safety guarantees that we can give for those services. So an emergency braking capability could be, for instance, subdivided in terms of their safety guarantees by guarantee that we have a stop distance below a certain threshold. This means like if we are below 10 meters, this is quite good, very good, effectively, depending apparently on the features. But in order to be able to guarantee this kind of quality for the emergency braking capability, there would be some preconditions that that we have found during design time engineering, where we're saying, okay, well, this is only possible if we have like a very good, so dry road, for instance, if we have a good braking system involved, and other, also runtime evidences that occur at the same time. So, and if we are monitoring those based on the monitors that we have defined here, then we can kind of at runtime evaluate this Boolean logic here and come out that this guarantee is true. And kind of building different equivalence classes on these parameters that we have defined to influence the guarantee, then we come to a little less performance guarantee here, so which would force us to drive with a larger distance. But actually it would prevent us from having the usual case that is nowadays the case, where we say, well, if something happens, we are going, so to say, fail safe and deactivating our functionality. And concerts, so conditional safety certificates, as the name says, it allows us to define arbitrary many variants here in order to stay at least with a degraded functionality still operational. So the real power of this approach lies in the fact that we have these intermediate guarantees that kind of do not force us to shut off, but to stay still operational, but with a degraded performance. And there are also, as I indicated already, is the possibility that to get a better idea about those values and about the confidence that I need in those values, I can also use and specify safety demands that I can, at runtime, I can compose different of these models from different systems, so to say. This would mean this is equipped, or the cloud would have a concert defined in terms of guarantees, what it can guarantee, for instance, for the weather forecast or something like this, or the road state, like in terms of mu, what the red car sees. And in the end, we will get, so to say, then kind of much more confident information about what in the end constitutes our safety guarantees. One note about this, it may look very easy here to have like two variants defined that is dealing with certain influences, but behind each variant we have the full stack of design time safety life cycle that we need to do. So effectively, this is just a variable safety concept, and if we're looking that we need what we need in order to derive a proper safety concept and to validate it, then actually each of those variants should be carefully chosen, whether it really gives the performance that we need, so to say. And so just that this is not just an easy model, so to say. It's just what is the result of the stuff. So we want to not shift everything into the runtime, but just like having some variables that we want to resolve. Okay, I will skip over that and just show you how this concert works in practice, if it works. So what we are seeing here is, so to say, a platooning scenario where we have cooperative functionality in this case, and here down we see, so to say, concert models of both vehicles, so to say. And what we are showing in this CARLA demonstration here is that if we kind of influence certain kind of failures or bad weather, like it was in this case, then we are kind of reasoning with those Boolean concert models, so to say, coming up with different safety guarantees that are possible, and in the end kind of switching between the variants that we are having. So in this case, we are injecting an ESP failure, which leads us to have a less confidence in our speed value, meaning like we need to accept more failure for certain deviations, and this constantly then leads to the fact that we have a variable safety guarantees. Medium capability here means we need to keep a larger distance. And this is actually what the demonstration here is about. In case the video quality was not so cool, just feel free to go to the YouTube video to look at it. Last but not least, I want to talk like very quickly about the design time safety engineering aspect. So the models that I've just shown, these Bayesian risk models and the concept models, they don't come out of nothing, but they have, as already indicated, the whole design time safety engineering backbone behind it. So for each of those models, we need to really make sure that, that actually we have proper engineering methods in place that will result in those models, and that the models are sufficiently capable of being consumed by the car then in a fully formal manner. And yeah, how we at Fraunhofer approach this. So for the design time aspect, we have a design time engineering toolchain that's called Safety Box, which actually allows us to produce those runtime models in an assurable manner. So what comes out in the end is a safety argument, along with the evidence required that we have the right models for doing the right tasks. And under the runtime component that we are having, so to say, it's called a safety supervisor, where we have realized based on the ROS framework, so to say, yeah, runtime components that are able to consume those models that we were producing at design time semi-automatically, and then let them run to, so to say. So coming to the conclusion, what is very important in order to make this dynamic risk management concept work is that we need formal definitions of what safe operation means in terms of behavioral safety in the absence of failures. And yeah, based on such a definition, we can then decide what are the situation-specific factors that we need to monitor in order to get an idea about dynamic risk. On the other side, we can use conditional safety certificates to yeah, express variable safety concepts that kind of allow us to get an idea what the currently available safety capabilities are for our ego vehicle. In order to make this yeah, dynamic risk management control run, we also need to be aware that we need systematic design time engineering to make sure that our runtime models are sufficiently safe. And not to forget that actually this yeah, dynamic risk management framework is dealing a lot with behavioral safety, but that does not relieve us from making sure that actually safe operation in presence of failure is also assured. So this is a precondition, and functional safety needs to be assured at all. And if we did all of these kind of things, then we can use the dynamic risk control aspect to compare, on the one hand, dynamic risk with the dynamic capabilities that we have. And this enables us to really control the system behavior to be just below the residual, so the acceptable risk, so to say, but still achieve a situational optimal performance. And that is the goal that we saw in the initial video. And this is where I would like to close my talk for today. Thanks.
Thank you, Jan. Thank you for the presentation. Of course, well, also very good with get in touch. So, of course, if you have further questions, feel free to reach out to Jan after the conference as well, or throughout the other sessions. But of course, let's go on with our little Q&A session. So one question we got was actually, were there any use cases for this concept where this is applied already, or is this rather theoretical or simulation based so far?
So yeah, so those concepts, they have been evaluated already. Like, as I said, the concepts part was evaluated already like since 10 to 12 years in agricultural scenarios where we had tractor implement runtime integration already. And yeah, so the dynamic risk assessment was so far is actually more on a theoretical basis, because it was like, it is developed since like 4 or 5 years only. So we had like 2 PhDs running in this area. And yeah, mostly we are dealing with scenarios in the automotive domain. So we saw this platooning, for instance, but we didn't have an evaluation of that in the real world. But that would be definitely something that that we are searching partners for at the moment. So I think from the research perspective, we have a lot of evidence that this concept will make sense, and also based on the feedback that we got from industry. So kind of we integrated that already in the research, but now the next step would be like to apply it on a real world basis.
I mean, like the follow-up question, which is basically a part of that, is, but how extensively have you done simulation testing then?
Sorry, I didn't get it because
Sorry.
it was.
So how extensively were there simulation testing? Like we saw a lot of videos already. I think it's just about the amount and the extensivity of those simulation testing when it comes to the models of the risk management.
Yeah. So regarding the simulation testing,
Mm-hmm.
I wouldn't say that actually this dynamic risk management component is something that should be like verified differently than than nominal controller that is validated and verified nowadays. Yeah. So the most apparent difference between the dynamic risk management component and actually conventional nominal safety controllers is that we are trying to not use like any AI-based perception in those cases, but that we are trying to keep the runtime safety models as easy as possible so that we can validate them by conventional means. And that means like we are dependent actually on approaches for finding those, let's say, complete situation categories that the predecessor talk mentioned. Yeah. So I personally believe that in the end there will be like certain scenario catalogs because that has been done also for ADAS functionalities in the past, that we say we have a definitive catalog of scenarios that your system needs to operate in safety. But the big question that I'm also researching in a big German research project right now that's called VMV methods is actually what that scenario catalog should be and how it is derived with a respective confidence.
Okay, well, I would say thank you very much. Thank you also for the answers and the presentation.